Now we want to do a reference circle picture, so here's a reference circle. It turns out that the radius of this reference circle is the amplitude, which we've just calculated to be 5 centimeters. Now let me emphasize that we've just got a big old coincidence going on here. The hypotenuse of this triangle we used in calculating the cosine of the arctangent of -4/3 happens to be 5. That has nothing to do with the fact that we have an amplitude of 5 centimeters. Okay, remember that this whole inverse tangent thing was done before we ever considered the amplitude. Okay, so theta naught is the inverse tangent of this. That just happens to be an angle when we plug in our value of omega that gives us a triangle here whose radius is equal numerically to the 5 centimeter radius of our reference circle, the 5 centimeter amplitude of our motion. Had the pendulum been started at the 4 centimeter position, we would not have gotten 5 centimeters here, but we still would have gotten this triangle. So the two are completely independent. Had this been 4 centimeters, this would have been 20/3, 6 2/3 centimeters, would have had nothing to do, no apparent relation to this triangle. So this is just a completely unpredictable coincidence of the numbers. That this number happens to equal this number. This doesn't have any units, so this quantity is not at all equal to this quantity, and never should be expected to be. Okay, this triangle is just a device that we use to evaluate the cosine of an arctangent. Okay, well, hopefully that's clear. So we have a 5 centimeter radius here, and we have an initial angle, inverse tangent of 4/3. What's the inverse tangent of -4/3? What's the inverse tangent of -4/3? Well, that would be, and just coincidentally on this triangle, it just happens to work out real well. If we go -4 in the y direction and 3 units in the x direction, and that would be centimeters, totally unrelated. Well, not totally unrelated to these numbers, but the fact that this is 4 and this is 3, remember, depends on the fact that we started at the 3 centimeter position. Had it been 4 centimeters, then these numbers would not have been 4 and 3. But they would be in the proportion of 4 to 3, and this would be negative and this would be positive. So that gives us a point down here on the reference circle that's consistent with the inverse tangent of -4/3, which again is our theta naught, our initial angle. So that would be consistent with a motion that starts here. This would be our r of 0 vector. And then we would start doing our oscillation, going around the reference circle at velocity, angular velocity omega. So our angle at any time would be this plus omega t. So omega t would be the angle measured from here. There's another angle that's consistent with the inverse tangent of -4/3, and that's the one that's diametrically opposite up here. So maybe we start on the reference circle at this point, maybe we start at this point. Which point is it? Well, remember our initial condition was that our initial velocity be positive 20 centimeters per second, and our initial x position be 3 centimeters. Okay, well, our x position works out just fine. If we project this vector up here, we get a 3 centimeter position on our x-axis. We have a velocity of 20 centimeters per second, so we're moving, excuse me, we have some velocity on our reference circle, so we could do a velocity vector. Let me kind of color code that, put that one in yellow. Here's our velocity vector. Now that's a velocity on the reference circle. Its projection is the velocity that the oscillator actually has. Okay, so here's the velocity of the oscillator. Here's the velocity of our reference circle. We don't really have to, of our point on the reference circle, we really don't have to figure this out. What we know is this should be 20 centimeters per second. Now, if our initial R is back here, which is again consistent with the inverse tangent negative 4/3, then we would have a velocity, reference velocity in this direction. And our projection of the reference velocity would be here. And this would have to be 20 centimeters per second. But it can't be because this is negative. This can be 20 centimeters per second because it's positive. Okay, so this is not positive, so we reject the assumption that led to this, which is that the initial point in the reference circle is here. This is positive, so it's perfectly possible. And since we only have two choices for where the reference, for where the R vector for our reference circle starts, either here or here, and we've rejected this one, we're left with this one. So we have to start at this point on our reference circle. So what's our x of t function? Our amplitude is 5 centimeters. It's a times the cosine of omega t plus theta naught. It's 5 centimeters times the cosine of omega t. Omega is 5 radians per second. Excuse me, the chalk isn't working real well here. Yeah, it's probably me that's not working real well. 5 radians per second times t plus the inverse tangent of negative 4/3. Now, if you remember what you should have learned in trigonometry, the inverse tangent of negative 4/3, and if you punch it into your calculator, you'll see this, is a negative angle. Angles are measured in the positive direction, but if you have a negative angle, that means it's going to be measured in the other direction. So this angle from here down to here is the inverse tangent of negative 4/3. And that comes out something like 55 degrees or something like that. You can work that out if you want it in degrees or in radians. It's pretty close to negative 1 radian. Then the picture is kind of consistent with that. So there is your final solution for the position function of this oscillator under these conditions. It starts at position 3 centimeters with a velocity of 20 centimeters per second. Amplitude is going to be 5 centimeters, and the motion, well, if we start here moving around in this direction, that means we first move out to here, then we move back through equilibrium, and so forth. So, we're starting not at equilibrium, we're starting 3 centimeters out from equilibrium. We go to start, and it oscillates like this. Giving it that start, it goes out to the 5 centimeter position, comes back through the origin, back to the negative 5 centimeter position, and continues oscillating in that manner. It's very useful to do a graph. I don't have a lot of room. I'm going to have to try to do a very small graph here, but hopefully you can see. We got a graph with a y-axis and a t-axis, or an x-axis and a t-axis. And we got 5 centimeters marked here, and we know that our oscillation is going to go from negative 5 centimeters to 5 centimeters, negative 5 centimeters, 5 centimeters. I didn't label the negative 5 centimeters. I didn't have room, but that should be understood. Our initial position is 3 centimeters. So when t equals 0, this being our t-axis here, make that a better t, we're at 3 centimeters, so that would be about here, a little closer to 5 than to 0. And now we're giving it the 20 centimeter velocity. That's going to take it out to the 5 centimeter position. So our position is going to increase up to 5 centimeters. So we're going to do this. So we increase up to 5 centimeters, and I hope you can see that. But then, as the reference point continues moving around the circle, we're going to decrease back to 0 and then to negative 5 centimeters. And that's going to go like so, and then we're going to start coming back to the right, which means our position is going to increase back up towards 0. And then when we get through this point, we're going to go right through 0 and start another cycle. The cycle starts here, ends here when we get back to our initial 3 centimeter position, or this inverse tangent of negative 4/3 position on the reference circle. And then we just go on as long as the oscillation continues. So just for a quick summary, what do? We identify the initial conditions. That's really fairly easy to do in this situation and in most situations. We get two simultaneous equations. We know what our x of t function is. We take its derivative, we get our v of t function. We plug t equals 0 in and set our function then equal to 3 centimeters. And that's going to give us this equation. And then our v of 0 equals 20 centimeters per second gives us this equation. Then we proceed to solve the equations to find A and theta naught. That's a little bit, when you're not real familiar with this, it's easy to get kind of lost in the calculations, but we want to keep track of what all this means. So we probably want to draw our reference circle at some point. But running through the pre-calculus of the trigonometry and everything else and doing the solutions, we end up with the angle arctangent of negative 4/3 and 5 centimeter amplitude. We put that onto our reference circle and interpret it and sketch the graph. Also, of course, we write down our function. The graph represents this function. The reference circle picture represents this function.